So, Jai Hind, my name is Ritesh Sharma. I am from Akgec Engineering College, Ghaziabad. So, I am taking subject Fundamental of Electrical Engineering in first year. And today I am going to take the topic the three-phase induction motor, in which we will discuss about the torque equation and the torque slip characteristics of the three-phase induction motor. So, in the previous lecture, we discussed about the principle of operation of the three-phase induction motors. So, we know that whenever the three-phase stator winding is energized a three-phase supply, the rotating magnetic field is set up, which we have already discussed in our previous section, and the speed is given by this 120 F by P. This is the speed. The speed of this rotating field is given by 120 F by P, which depend upon the frequency and the number of poles, where P is the number of poles and F is frequency, and we call it the synchronous speed. Now, when this stator magnetic field is rotating, and it will pass through the rotor winding. The rotor is stationary actually, and the rotor, when the flux is linked with the rotor conductors, it will induce some voltage. There will be some voltage because of Faraday law. The voltage will induce in the rotor winding, and consequently the current will flow in the circuit because the rotor conductors are short circuited. Now, what happens when the current will flow? We know that when the current conductor placed in the magnetic field, it will experience a force, and because of this force or the torque, your rotor start rotating in the direction of stator flux. That is called the rotating magnetic field. Now, the reason for this, that why the rotor start rotating in the direction of the stator flux, because it will experience a Lenz law, because of Lenz law. So, Lenz law said that the cause opposes the effect, and the cause is the relative motion between the stator magnetic field and the rotor flux. So, that means you can say that the rotor will try to rotate in the direction of rotating magnetic field, whether it is clockwise or anti-clockwise. Now, this is the principle of the three-phase induction motor. Now, next is that when the rotor starts rotating with this, now your rotor is always rotated with the speed less than the synchronous speed. That is, and here the term is called the slip. The slip is nothing but it is the ns minus n upon ns. This is the slip, or it is the relative speed between the synchronous speed and the speed of the rotor. So, this is the basic terms called the slip of the three-phase induction motor. Now, the slip of the the slip of this induction motor means that your rotor is rotating with the speed less than the synchronous speed. It means the rotor may our rotor will rotate at the synchronous speed. So, you can say that when the rotor rotates at synchronous speed, there will be no induction, because there is a zero relative motion, and because of this relative motion, there is no relative motion, no induced EMF, no current will be there. So, you can say that your rotor will rotate but less than the synchronous speed. That is why this motor is also called asynchronous motor. So, this is the slip of the in the three-phase induction motor. Now, let us come to torque equation. The torque equation, before starting the torque equation, let us understand that when the slip is there, you can say that the the frequency of the rotor current. Now, the frequency of the rotor current, we know that the frequency is given by 120 ns, or you can say that the speed is given by, rather you can say that the speed is given by ns is given by 120 F by P. It is in RPM. This is the speed of the synchronous or rotating magnetic field. We call it the synchronous speed. It means that the frequency is equal to Pns upon 120. This is the, Now P is the number of poles, which is almost constant, okay, throughout the operation. So you can say that the frequency is proportional to what? Speed. Here frequency is proportional to speed. So if the speed is constant, the frequency is also constant if we need to keep. Now similarly, you can say that when the rotor is rotating with speed n, the relative motion is ns minus n. So frequency will depend upon that speed. So that means that the frequency of the rotor current, or you can say f dash, will be equal to or proportional to ns minus n, which is the relative speed between the rotating field and the rotor, because the rotor is rotated at n speed. So from this relation, we can say that the frequency of the rotor current upon f ns minus n upon ns, which is nothing but it is a slip. So hence you can say that the frequency of the rotor current is given by f dash, or you can say that is given f dash is equal to s times of f, where f is the frequency of the stator field. Whatever supply that we are giving to the stator field is the frequency f. Okay, so this is the frequency of the rotor current. Okay, so now torque equation. The torque produced by the three phase, when the torque produced on the rotor conductor or the rotor is depend on the three factors. First is called the magnitude of the rotor current, that is called I2, the magnitude of rotor current. Here we can take that this rotor winding is again it's a three phase winding, so we can take it as three phase. So the current is in the phase current, the rotor current. Secondly, the flux which interact with the rotor of the three phase induction motor. Whenever flux will be there linked with the rotor conductor, that means the flux which is interact with the rotor. And the third one is called the power factor of the rotor of the three phase induction motor. So when we combined all these three factors, is called the current, rotor current, the flux and the power factor. The torque is proportional to flux, rotor current and the rotor power factor. So torque is proportional to this, and where a flux, you can see that this flux phi is nothing. We know that this flux is proportional to E1, because this flux which link with the winding of the stator will produce the voltage induced EMF E1. Then this, because of the transformer action, the E1 or the E2 will induce the voltage, because the flux is linking with the rotor conductor. The voltage induced in the E2 will be also proportional to the phi, because the same flux is linking with the this. So you can say that E2 is almost proportional to flux. So it means that the current I2 will be given by, if E2 is proportional to flux, so you can say that this torque is again is given by this phi into I2 into cos phi 2. So to find this torque, we need to also calculate the current, how much current is flowing in the our rotor conductor. So in rotor conductor, S is a slip, the running or the induced EMF or per phase induced EMF is given by SE2, that S is the slip. So I2 will be given by voltage induced EMF upon the per phase impedance of the circuit. So Z2 is the per phase impedance. So total impedance Z2 on the rotor side is given by this. So I2 is the current this. And the total impedance Z2 on the rotor side is given by Z2, because Z2 is the per phase impedance. So it is nothing but an impedance or at when the rotor is rotating at some speed. So if we put this value, you will get I2 will be equal to S times of E2 upon this impedance. This is the current I2. So this is how we can evaluate the value of current. Next is the power factor. So power factor can be calculated. We know that the power factor is given by the ratio of the rotor resistance to the rotor impedance, and the impedance can be written by this factor this equation. So the torque equation or the torque is given by this whole equation or this one. So this is the current, this is the current, this is the power factor, this is the voltage induced in this. Now this is the constant is given by this 3 upon 2 pi ns. So this is the torque equation is given by, finally the torque equation can be given by, from this previous equation, torque is 3 upon 2 pi ns SE2 square R2 upon R2 square plus SX2 square Newton meter in Newton meter. This is the torque equation of the three-phase. Now this term is almost constant. This term is almost constant. So you can say that the torque is proportional to SE2 square R2 upon R2 square plus X2, where R2 is the rotor resistance per phase and X2 is the rotor reactance per phase, and X2 is the rotor reactance when the rotor is running at some speed with slip S. So this is the torque equation. Now to draw the torque slip characteristics, for torque slip characteristics, now write down next is with this torque equation we need to evaluate, or we need to draw the torque slip characteristics. So the torque slip characteristics, so you can write down the torque slip characteristics. Torque slip characteristics. In torque slip characteristics, first you can say that first the torque equation is given by, as I just write in the previous, the torque is proportional to SE2 square, I am just writing it again, upon R2 square plus SX2 square. Okay, R2 square plus SX2 square. This is the torque equation. Now, whenever we draw the torque slip characteristics or the torque in three-phase induction, the operation, it can be divided into the two regions. One is called the low slip region and one is called the high slip regions. So first we take the case of low slip region. So in case of low slip region, where the slip is very, very low. Okay. So low means when your rotor is rotating nearly the synchronous speed, but less than synchronous speed. So when the slip is low, this resistance term or R2 square is quite or larger than this value at low slip region. So at low slip region, this resistance R2 square is very, very large than SX2 square, and because of this the torque will be given by this SE2 square R2 upon R2 square. That is almost is proportional to the S, or you can say the torque is proportional to the slip, almost linear actually, because this E2 again it's the induced EMF in the rotor winding, again it's a constant, R2 is a constant. So here you can say that the torque is proportional to slip. Okay. Second case, in second case for high slip region, for high slip region, this term SX2 square in this is greater than R2 square. So this S2 square is greater than R2 square. So you can say that when this term is greater than this one, okay, so this might be equal to the torque will be given by or inversely proportional to slip, because here you can say that x2 is again constant, r2 is again it will be neglected. Then you can say that S is inversely proportional to the slip S for high slip region. So two regions that we have. Now let us draw the torque slip characteristics. The torque slip characteristic. So this is our slip, and in the y-axis we will take the torque. Okay. So initially when the slip at this position S is equal to 0, and here suppose that S is equal to 1. S is equal to 1. S is equal to 0 means what? When your rotor is here, which is rotating at ns speed, and here the speed is 0. So starting. So initially when slip is very low, you can say that it will be linear. The torque is proportional to this slip. So initially it will be a linear like this. And when it reaches some value or at high slip region, it will again behaving like the torque is inversely proportional to slip. So it will be go like this. You can say like this. So this is the maximum torque. This is called T max. That is the maximum torque, and this is the slip at maximum torque. Here we have the starting torque. That is the starting torque means what? When your rotor is a standstill, that is the 0 speed. When the slip is 1, and this is maximum torque. So these are the two region. We call it the low slip region, and this is the high slip region. Okay. So this is, you can write it here, the torque. This is the low slip region, and this is the high slip region. It is almost hyperbola, high slip region. And this the linear region, or the low slip region is the operating region of the three-phase induction motor, in which your induction motor actually operate. And this high slip region, or it's a unstable region. It is low slip region, or also called the stable region. And this is the high slip, which is unstable region. Okay. So this is the torque slip characteristics of the three-phase induction motor. So here you can see that the slip is increasing like from 0 to 1. So these are some torque slip characteristics of the three-phase induction motor. So this, now if you see the torque slip characteristics, or you can say the effect of resistance on the torque slip characteristics. So suppose that this is the torque slip characteristic at some resistance value R2, and if we need to then suppose in the case of phase wound or the slip ring induction motor, we can insert the resistance of in the rotor or rotor resistance. So we can add or change the rotor resistance so that the torque can be increased. Okay. So the effect of, write down, effect of rotor resistance effect of rotor resistance on torque slip characteristics. Okay, so let us draw the torque slip characteristics for so this is, suppose we have a slip and this is the torque. So first of all, let us draw the torque slip characteristic at some resistance value of R2. So suppose that the torque slip characteristics is given by so this is S is equal to this is S is equal to 0, S is equal to 1, 1. This is the maximum value of this. This is the maximum value of this, that is T max. Okay, so T max is there. So you can say this is the maximum value. So at certain, this is the at low region, this is the high slip region. So this is the for particular value of resistance R2. Okay. Now if we change the value of resistance, suppose if we insert more resistance in the rotor winding, so the torque slip characteristic will be changed accordingly. Suppose that at R2 dash R2 double dash and R2 triple dash. So here what is happening, the maximum torque is constant, same for all. Since the maximum torque is not depend upon the rotor resistance, when we calculate the maximum torque, that is the torque which is the maximum torque which is not depend on the rotor resistance. So although when you change the value of rotor resistance, it will not change. Yes, but the starting current, so the starting torque will change because the starting torque is proportional to rotor resistance. So these are the different value of starting torque for different rotor resistances. So this is the effect of rotor resistance. Here the resistance is increasing like this. So R2 is less than R2 dash, R2 dash is less than R2 double dash, and then R2 double dash is less than R2 triple dash. Means as we are going to increase the rotor resistance, only the Tmax will not change or maximum torque will not change, only the starting torque will increases. That is called T starting. Okay, so this is how you can say that the effect of rotor resistance on the torque of the three-phase induction motors. So this is all about in this lecture of the three-phase induction motor, the torque equation and the effect of torque and the torque slip characteristics of the three-phase induction motors. So thank you so much and